Hey friends, here we are, Geometry Friends, in chapter 6, and this whole chapter is all about quadrilaterals, which we know to be four-sided figures. We've been talking a lot about triangles, so we're getting into the four-sided figures this entire chapter, but we're going to start off section 6.1 speaking specifically about polygons and their angles. So our vocabulary begins with the concept of a diagonal. Let's first draw a polygon. So we know a polygon is a multi-sided figure. Three or more sides will create a polygon. That's not a great side, but you get where I'm going. And so if we would talk about the diagonals of this polygon, by the way, you see it has six sides. I'm hoping you know what the name of a six-sided figure is. Anybody? Okay, yes. Good. You raise your hand in the back. Yeah, very good. It is a hexagon. Excellent job. 20 points for Gryffindor. So, A, B, C, D, E, F is a polygon, particularly a hexagon, and we need to talk about what diagonals are. So, when we talk about diagonals, it really is the connecting of two vertices that are not adjacent. Adjacent means side by side. If I connect two vertices that are adjacent, I'm just drawing over one of the sides. So a diagonal requires that you're connecting vertices that are not adjacent, that are not next to each other. And so I'm connecting AC, AD, AE, and I can continue with this plan to continue to connect as many vertices as I can that are not adjacent to show where all of the diagonals are. I think I got all the diagonals there. All right, cool. I got a funky problem, by the way, that deals with diagonals. We'll talk about it the next time we meet. If you consider, if you consider for a moment some polygons that we're familiar with, the triangle, the quadrilateral, some four-sided figure, then you have a five-sided figure which we refer to as a pentagon, and the six-sided figure which we reminded ourselves of just now, which is the hexagon. Does anybody remember what a seven-sided figure refers to, or what we call it? I have a funny joke for this that nobody thinks is funny, but we in Philadelphia have the bus system SEPTA, and what do you say when you miss the bus? SEPTA gone. Get it? SEPTA's gone? Okay, fine. And it goes by two names, heptagon or a septagon, but this one's funnier, so I use it more often, though this one is, I think it's hepta, yeah, I got it. This one's also used. Anyway, so that's a seven-sided figure. We should know the names of all the figures up to a 10-sided figure. We'll talk about that in class. But if we were to talk about the angle measures of a triangle, you know that if I added up all the interior angle measures, I get 180 degrees. And so what I'm going to do is talk about creating a situation where you can see that if I were to, in this case, draw a diagonal in this quadrilateral, I break it up into two triangles. And these two triangles are not just any old two triangles. They're two triangles where their three angles mesh with the four angles of the polygon, right? So of the quadrilateral. So if I were to add up all the angles of one triangle plus all the angles of the other triangle, I would get the total interior angle sum of the quadrilateral, right? Which is 360. Now, what I don't want you to mistakenly do is say, oh, but you could make more triangles, lady. See, I make more, four. I don't want you to do that because the angles here do not overlap the angles of the quadrilateral. Therefore, having more triangles does not help us better count the angles of a quadrilateral. Do you see what I'm talking about? All right. Hopefully that made sense. I'm going to do the same thing here. Watch how I draw these diagonals. I think that three triangles work because the five angles, if I'm trying to get the interior angle sum of those five angles, I am going to need the angles of this triangle plus the angles of this one here plus the angles of this one over here to match up with the five angles that I'm talking about. Therefore, this is 180, The sum of these three is 180, and the sum of these three would be 180 as well. 180 plus 180 plus 180 is going to give me 540. All right, and I can continue this process. So what we're about to see is a little theorem, or really a little guide. It's a theorem. A little guide to figure out what is the sum of the interior angle measures of an n-sided convex polygon. Well, the polygons that we're dealing with are convex, meaning they don't have any interior angles that do something funny like this. Like this kind of interior angle. We don't have that. They're all the angles pop out or are are convex as opposed to concave, like the one I just showed you. So what I'm realizing is that you probably might have seen it already. Like with the triangle, there was one triangle. With the quadrilateral, there was two. With the pentagon, there was three triangles that I needed to create. And if we continue, it would make sense that within the hexagon, there's four triangles that fit neatly up against all the angles of the hexagon, right? So that, let me get a highlighter, so that if I add up these three angles plus these three and these three here and these three here, I'm going to have four angles of 180 degrees that I'll add up to find the interior angle sum of the hexagon. So we get an interior angle sum for our hexagon as 720. Finally, we could do the same thing for our heptagon or our septagon, and you could see that if I make these triangles, I'm going to make 5 triangles. So I'll be adding up 185 times, and you get how this is going, right? All right, good. Hopefully you do. 180 basically is just, this is just 180 more than 720. So 720 plus 180 is going to give me 900. And so the interior angle sum of a heptagon or septagon will be 900 degrees. So why am I showing you this? And we've got this cool theorem. Well, this cool theorem is best demonstrated by what we just did. If you have a certain number of sides, let's say a pentagon, which has 5 sides, if you subtract 2 from the 5 and multiply that by 180, you'll get the interior angle sum of 540. Let's look at our picture one last time. So this is a 5-sided figure. Subtract 2, you get 3 triangles. Here's a 4-sided figure. Subtract 2, 2 triangles. 6-sided figure. Subtract 2, 4 triangles. And 7-sided figure, and so on and so on. When you subtract 2, you multiply by the number 180 to get the interior angle sum. Hopefully that makes sense. So the first one says find the sum of the measures of the interior angles of a convex heptagon. We know a heptagon, better known as a septagon, has 7 sides. So the formula says to find the interior angle sum, I'm going to write it in abbreviation, interior angle sum. What we're going to do is take n minus 2, multiply that by 180. And when I take n, in this case, it's going to be 7 minus 2, which is 5. I'm going to multiply that 180. I know we just did this, guys, but it's kind of cool to use the formula. We get 900 degrees. So the sum of the measures of the interior angles of a convex heptagon will be 900 degrees. Let's do this one here. Find the measure of the interior angle of a quadrilateral. Well, we just went through the process of realizing that the sum of the interior angles of a quadrilateral would be 360. How we get it? Let's use the formula. Remember, n minus 2 times 180 is going to give me the interior angle sum. Well, what does n have to do with this? What is n here? It's going to be 4. So 4 minus 2 times 180, 2 times 180. You see where I'm going? 360. Okay, so all of these angles add up to 360. Big deal. Yes, super huge deal. So 360 is equal to 3x plus x plus, sorry, that wasn't a plus sign, plus 90 degrees plus another 90 degrees. And like all algebra problems, we like it when it only has one variable, which is x in this case. So 4x plus 180 is equal to 360. If I subtract 180 on both sides, I'm going to take this up here. I get 180. That's 360 minus 180 is equal to 4x. I'm going to divide both sides by 4, and you know what happens? X is equal to 45. And since x is equal to 45, this angle has to be 45 times 3, which is 135. And I've answered the question. Let's go ahead and look at this guy. The poles for a tent form a regular hexagon. This word, I don't remember if we talked about it. Regular means special in that it means all of the angles are congruent, they're equal, and it means all of the sides are equal. So anytime you're talking about a regular polygon, you're talking about a polygon where all the angles are equal and all the sides are equal. Now that that has happened, we know that it's a six-sided figure. Let's try to answer this question. When the poles are properly positioned, what is the measure of the angle formed at the corner of the tent? Well, first what we're going to do is find the interior angle sum. And then we're going to divide it by the number of sides. And the reason why we're going to do this is because we know that each of the angles here are equivalent. So if I find the sum of all the angles and divide it by the number of angles or sides, which is the same thing, I'll get the angle for one of them, right? I'll get one angle. So this isn't too bad. We know that the interior angle sum is n minus 2 times 180. And then to find a specific angle, we're going to come back and divide by n, the number of angles. So using that logic, what we'll do is we will write down 6 minus 2 times 180 over 6. Remember, this 6 is because we're going to get the interior angle sum, then divide to find one specific angle, right? So 6 minus 2 is 4 times 180, and we're going to divide by 6. And as you know, since this is all being multiplied, and this is like multiplication and division, I can't help myself out by dividing 180 by 6, because I know 18 divides by 6. So I'm going to get 4, 6 goes into 18 3 times, so 6 goes into 180 30 times. 4 times 30, which is easy for me to do, which gives me 120. So what I know is that I have an angle here that's 120 degrees because I found the interior angle sum, then divided by the number of angles because I was dealing with a regular polygon.